Hello, math fans. Right, so now we're going to approximate the function f of x equals cube root of x by a second-degree Taylor polynomial centered at a equals 216. We're going to follow that up by asking how accurate that approximation is when x is between 211 and 221. Now, that seems like a really random thing to do, to pick values of x that are between 211 and 221, but the idea is that the Taylor polynomial is centered at 216, and we want values of x that are only 5 units away from the center of the polynomial. So it's not really all that random. Okay, so we need the formula for the second order Taylor polynomial centered at x equals a. It looks like this: f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. So that means we need to compute two derivatives of the original function. Okay, so we're starting with cube root of x, and we're rewriting that as x to the 1/3. If we take one derivative of that, we get 1/3 x to the minus 2/3. So remember, we bring the power down, subtract 1 from the power. And then we're going to do that again for a second derivative, bring the power down, so we have the negative 2/3 out in front, times 1/3 x to the minus 5/3, because we subtracted 1 from the power. And then, of course, we can combine the coefficient into a single coefficient, x minus 2/9 x to the minus 5/3. All right? So the next thing we need to do is we're going to plug in the center, which is a equals 216, into these derivatives. So we start with f of 216, and that's cube root of 216. And 216 was chosen because it has a nice cube root that just works out to be 6. We highlight that in red, and we're going to do that for the value of the function and the value of the derivatives at 216. Okay, so the next thing we got to work out is what is the value of f prime at 216. So we go back to our derivative, which we computed here, and then we're going to plug in 216 into that, so we get 1/3, 216 to the negative 2/3. In order to work this out, because we have a negative exponent, we'll move that down into the denominator, and then we're going to rewrite this so that the 216 to the 2/3 is actually 216 to the 1/3, and then we square that whole thing. That works out nicely because 216 to the 1/3 power is just 6, and then we square the 6, and then 6 squared is 36. It all works out to 1 over 72. So that's f prime at 216. Okay, so now we're going to do the same thing where we're going to take 216 and now plug it into the second derivative, which we had computed here. Okay, so if we plug things into the second derivative, plug 216 into the second derivative, we're going to get negative 2/9 times 216 to the minus 5/3. And we're going to do the same trick again where we move that down into the denominator, and then we'll rewrite that again as 216 to the 1/3 power, with that whole thing raised to the 5th power. Okay, so that works out rather nicely because we get 6 to the 5th power. All right, now that's a bit of a mess. You can plug all this in your calculator if you like. 6 to the 5th power is 7,776. That's kind of a cool number. And then if you simplify this whole expression, so I'll leave you to work this out, you end up getting something that looks like this: negative 1 over 34,992. Okay, now we're going to plug everything in to the formula for the second order Taylor polynomial, and we get something that looks like this. Okay, f of 216 plus f prime of 216 times x minus 216 plus f double prime of 216 over 2 factorial times x minus 216 squared. Okay, and now we have the values of the derivatives that we had computed, and so we just plug them in there. And so this is it for the first part. We've now computed a second order Taylor polynomial, and this can be used to approximate the value of the cube root of x. Okay. So the next thing we want to do is answer our follow-up question, which is to try to put a bound on the remainder term for this, for values of x between 211 and 221. So we want to know how accurate the approximation is. So what we use is the estimate of the remainder that we got from Taylor's theorem. And let me remind you what that theorem said. It said that if you have a bound m on the n plus first derivative, specifically what we're saying is that the n plus first derivative in absolute value is no bigger than m, as long as the value that you're plugging in is between a and x, then what we can say is that the remainder for the nth order Taylor polynomial centered at a satisfies this inequality. And so this will be the upper bound that we're going to try to find. Okay? All right, so in the theorem, what we're doing is we're using n equals 2, because we're doing a second order Taylor polynomial, and we're using a center of 216. So what the theorem says is that R2, the remainder after you compute a second order Taylor polynomial, is no bigger than m over 3 factorial times x minus 216 cubed. So you should be able to see the 3 factorial coming in from here, because we're picking n equals 2. And then you should see the x minus 216 cubed, this part of it here, coming from this guy. Again, picking n equals 2 and a equals 216. Okay? So here, remember that m is an upper bound on the absolute value of the third derivative. So at this point, we really need to compute what the third derivative is. So just to remind you, we computed this, the second derivative, negative 2/9 x to the minus 5/3. And so what we need to do is take one more derivative, and it's going to look like this. Now I've rewritten it a little bit. So if we have that x to the minus 8/3, I'll put that down as a fraction. So it looks like this. By the way, if you need to remind yourself how to get that derivative, so to go from here to here, we're just, again, taking the power, moving it back out in front, and subtracting 1 from the power. Okay? All right. So now, just to remind you that we're trying to see how accurate this approximation is for x between 211 and 221. So we need a bound on the third derivative. Now notice that the third derivative, which we computed here, is a decreasing function, right? As x gets bigger, this whole thing is going to get smaller. Since f triple prime is a decreasing function, then we can put a bound on that function like this. So here's our third derivative, and it's actually going to be smaller than the same thing but with a 211 plugged in. If you have a decreasing function, then the biggest that it can be is the value at the left endpoint of whatever interval you're dealing with. The left endpoint we're using is 211. Okay? Now if you work out this number, it's a big mess, but it turns out it's something that looks like this, about 2.35 times 10 to the negative 7. Okay? So this number that we've computed here, this is going to be our value for, that's going to be our value for m. Okay, so that gives us our value for m. The other thing that we get is that we have a value, we have that x is supposed to be between 211 and 221, and so we've got that the absolute value of x minus 216, so this expression here, has to be no bigger than 5, because you're no farther away than 5 from the center. All right, so we're now ready to put all of this in. That gives us our final estimate that this inequality, which we got out of the remainder estimate from Taylor's theorem, is smaller than, well, the m was smaller than 2.35 times 10 to the negative 7. We've got the 3 factorial, that's just the 6 here. And then we've also got that this expression here is no bigger than 5 cubed. So both of those are cubed. And so if we work out that whole thing, we finally get a bound of about 3 times 10 to the negative 5. So as long as we pick values of x that are no farther away than 5 from the center of the Taylor polynomial, we're going to have a bound on the accuracy. You will be no farther away than 3 times 10 to the negative 5. All right, that's all for now.